Let me tell you something that sounds absolutely crazy. Everything you see around you right now, this room, the chair you're sitting in, the cup of coffee on your desk, your own hands, all of it, every three-dimensional object you've ever touched or tasted or loved may be a kind of projection. A hologram. Not the flickering sci-fi kind you see in movies, something far more profound and far more unsettling. The entire three-dimensional universe, with all its galaxies and black holes and people, may be fundamentally equivalent to information written on a distant two-dimensional surface, the way a hologram on a credit card encodes a three-dimensional image on a flat piece of plastic. And I don't mean this as a metaphor. I mean it as a precise mathematical statement about the nature of reality. I'm Leonard Susskind. I've been a theoretical physicist at Stanford for over 50 years. I helped develop string theory. I fought a 25-year war with Stephen Hawking about whether black holes destroy information. And along the way, together with Gerard 't Hooft and later Juan Maldacena, I helped develop this idea, the holographic principle. It's one of the strangest things physics has ever produced, and I want to explain to you why so many of us now believe it's true. Not because it's elegant, though it is, not because it's fashionable, though it has been, but because the physics demands it. Hard, cold, unforgiving physics. Let me start where this all started, which is with black holes. You might think a black hole is just a region of space where gravity is so strong that nothing can escape. That's correct as far as it goes, but it misses the real story. The real story begins in 1972 with a young physicist named Jacob Bekenstein, who was a student of John Wheeler at Princeton. Bekenstein asked a question that at first seemed almost naive. He asked, does a black hole have entropy? Now, entropy is a measure of how much information is hidden inside a system. If you have a box of gas, the entropy tells you how many different microscopic arrangements of atoms could give you the same macroscopic appearance, the same temperature, the same pressure. High entropy means lots of hidden information. Bekenstein's question was, when you throw something into a black hole, a book, a computer, a cat, does the information it carried just vanish? Because if it does, that violates the second law of thermodynamics. Entropy in the universe must always increase or at least stay the same. If information disappears into a black hole, entropy decreases and the second law is broken. Bekenstein proposed that black holes do have entropy, and that this entropy is proportional to the area of the event horizon. Not the volume, the area. Think about that for a second. Normally, if you have a room full of gas, the entropy, the hidden information content, grows with the volume. Double the volume, roughly double the entropy. That's what you'd expect. But Bekenstein was saying that for a black hole, the information content is determined by the surface area of its boundary. A few years later, in 1974, Stephen Hawking confirmed this with a precise calculation. He showed that black holes radiate, they emit what we now call Hawking radiation, and that the entropy of a black hole is exactly equal to 1/4 of the area of its event horizon measured in Planck units. Let me be very precise about this. 1 Planck area is about 2.6 times 10 to the minus 66 square centimeters. That's unimaginably small. And the Bekenstein-Hawking formula says you get exactly 1 bit of information. 1 binary digit, 1 yes or no answer for every 4 Planck areas on the horizon. For a black hole with the mass of our sun, that works out to about 10 to the 77th bits. That's an enormous number, But here's the thing that should disturb you. It scales with area, not volume. Why should this disturb you? Because it suggests something very strange about the nature of space itself. If I give you a region of space, any region, not just a black hole, you might think you could pack an unlimited amount of information into it by making things smaller and smaller. You can't. Bekenstein showed that the maximum amount of information that can be contained in any region of space is determined by the area of the boundary of that region, not by its volume. This is called the Bekenstein bound. And what it means, if you take it seriously, is that the three-dimensional interior of any region of space contains no more information than can be encoded on its two-dimensional boundary. The interior is in some deep sense redundant. Now here's where it gets really strange. In the early 1990s, Hawking had been arguing for almost 20 years that black holes destroy information. His reasoning was straightforward. A black hole forms, things fall in, the black hole evaporates by emitting Hawking radiation. But Hawking's calculations showed that this radiation is thermal. It's random, like the glow of a hot coal. It carries no information about what fell in. So when the black hole is completely evaporated, the information is gone, permanently destroyed. This was a crisis, not a minor technical disagreement, a crisis, because the destruction of information violates one of the deepest principles in physics, unitarity. Unitarity is the quantum mechanical principle that says information is always conserved. The laws of physics are reversible. If you know the present state of a system with perfect precision, you can, in principle, reconstruct its past. Information can be scrambled, it can be spread out, it can be made practically impossible to recover, but it can never be destroyed. Hawking was saying that black holes violate this. I thought he was wrong. Gerard 't Hooft thought he was wrong, and we spent a long time trying to prove it. Let me tell you about the war with Hawking, because it matters for understanding why the holographic principle exists. Hawking is one of the greatest physicists of the 20th century. I don't say that lightly. His calculation of black hole radiation in 1974 was a masterpiece. But on the question of information loss, I believed he was making a profound error. The argument went back and forth for years. Hawking said the radiation is random. I said the radiation must somehow encode the information, even if we can't easily see how. The debate split the theoretical physics community roughly in half. Here's the analogy I used to think about it. Suppose you burn an encyclopedia. The ashes and smoke and heat radiation that come off seem random. They seem to carry no information about what was written in the encyclopedia. But we know from the fundamental laws of physics that the information is still there. In principle, if you could track every single molecule of smoke, every photon of light, every ash particle, you could reconstruct the encyclopedia. The information isn't destroyed, it's just scrambled beyond any practical ability to recover. I argued that Hawking radiation is the same, not truly random, but so thoroughly scrambled that it appears random. The information comes out, it's just very, very hard to decode. Now, to make this argument work, I needed to understand how information could possibly be encoded on the surface of a black hole. And this is where 't Hooft's insight became crucial. In 1993, Gerard 't Hooft, Nobel laureate, brilliant physicist, not someone who makes wild speculations, proposed something radical. He suggested that the physics of three-dimensional space could be completely described by a theory living on a two-dimensional boundary. He called it the holographic principle. The idea was that just as a hologram encodes a three-dimensional image on a two-dimensional surface, the real physics might be fundamentally two-dimensional, and the three-dimensional world we experience might be a kind of projection. When I first encountered 't Hooft's idea, I recognized it immediately as connected to what I've been thinking about with black holes. The Bekenstein-Hawking entropy formula was already telling us that information scales with area, not volume. 't Hooft was taking that hint and elevating it to a general principle about all of physics. In 1995, I gave this idea a more precise formulation using string theory. I showed that string theory provided a concrete mechanism by which the physics of a volume of space could be encoded on its boundary. The strings and the objects they form, membranes, what we call D-branes, naturally live on boundaries. The bulk physics, the three-dimensional interior, emerges from the boundary physics the way a holographic image emerges from the pattern on the film. But let me be honest, in 1995, this was still a conjecture. A well-motivated conjecture backed by the Bekenstein-Hawking formula and by suggestive results in string theory, but not a proof. The proof, or as close to a proof as theoretical physics gets, came 2 years later, in 1997, from a young physicist named Juan Maldacena. Maldacena's paper is one of the most important papers in the history of theoretical physics. It has been cited over 25,000 times. What Maldacena showed was a specific, precise, mathematically rigorous example of the holographic principle in action. He considered a particular kind of spacetime called anti-de Sitter space, a negatively curved spacetime like the inside of a saddle that extends forever. And he showed that string theory in this five-dimensional anti-de Sitter space is exactly equivalent to a particular quantum field theory, a conformal field theory, living on the four-dimensional boundary of that space. Not approximately equivalent, exactly equivalent. Every calculation you can do in the five-dimensional gravitational theory has a precise counterpart in the four-dimensional boundary theory and vice versa. This is called the ADS-CFT correspondence, and it's the most concrete realization of the holographic principle we have. Let me be very precise about what this means. It means that a universe with gravity, with black holes, with curved spacetime, with all the complexity of general relativity, is completely and exactly described by a theory without gravity, living in fewer dimensions, on the boundary. The gravitational physics in the bulk is not fundamental, it's emergent. It arises from the more fundamental boundary theory, the way temperature arises from the motion of atoms. Temperature is real, you can feel it, it can burn you, but it's not fundamental, it's a collective phenomenon. Maldacena's result suggests that gravity, and possibly all of three-dimensional space, is the same kind of thing. Real, but not fundamental, emergent. Now, I know what you're thinking. You're thinking, but our universe isn't anti-de Sitter space. Our universe has positive cosmological constant. It's expanding, it's de Sitter, not anti-de Sitter. And you'd be right to raise that objection. The honest answer is that we don't yet have a precise holographic description of de Sitter space. Maldacena's correspondence works beautifully for anti-de Sitter, but extending it to our actual universe remains one of the great open problems in theoretical physics. Some of us have ideas, none of us have a proof. That's intellectual honesty. But here's why I still believe the holographic principle applies to our universe, even without a complete proof. The argument from black hole entropy is completely general. It doesn't depend on whether the cosmological constant is positive or negative. Every black hole in every spacetime has its entropy proportional to its horizon area, not its volume. The Bekenstein bound applies everywhere. These are not features specific to anti-de Sitter space. They're telling us something universal about the relationship between information and geometry. And when multiple independent lines of evidence all point in the same direction, a physicist learns to pay attention. Let me address the most common misconception about the holographic principle, because it drives me slightly crazy. People hear the universe is a hologram, and they think it means the universe is fake, that nothing is real, that we're living in a simulation, or that the three-dimensional world is an illusion in the sense that it doesn't matter. That's wrong, completely wrong. The holographic principle doesn't say the universe is fake. It says the universe has a different fundamental description than the one our senses suggest. Think about a hologram on a credit card. The three-dimensional image you see is real. It has depth, it has structure, it responds to light. But the information that creates that image is encoded on a flat surface. Both descriptions are valid. One is more fundamental than the other. Here's another way to think about it. Consider a novel. The story has characters, locations, emotions, a plot that unfolds in time. These are all real aspects of the novel. But fundamentally, the novel is a sequence of letters on a page, a two-dimensional encoding. The story emerges from the encoding, but that doesn't make the story fake. The holographic principle is saying something similar about the universe. The three-dimensional physics we experience, gravity, motion, the cup of coffee cooling on your desk, is real. It's just that the most fundamental description of that physics lives on a lower dimensional boundary. Now let me tell you why this matters beyond the pure mathematics. The holographic principle has taught us something remarkable about the nature of space itself. In the old picture, the picture I grew up with, space was a stage, a fixed, pre-existing arena in which physics happens. Particles move through space. Fields oscillate in space. Space was the background, the container, the given. The holographic principle demolishes that picture. If three-dimensional space emerges from a two-dimensional boundary theory, then space is not fundamental. Space is derived. Space is something that the boundary theory constructs the way neurons construct the experience of color. Color isn't out there in the world. There are only electromagnetic waves of different frequencies. Color is how your brain represents those frequencies. In the same way, three-dimensional space may be how the boundary theory represents its own information. This has a profound implication. If space is emergent, then the connectivity of space, which points are near which other points, the very geometry we take for granted, must also be emergent. And in the last decade or so, we've begun to understand what generates this connectivity. The answer, remarkably, appears to be quantum entanglement. When two quantum systems are entangled, their states are correlated in a way that has no classical analog. Measuring one instantly tells you something about the other, regardless of distance. This was what Einstein called spooky action at a distance. He meant it as a criticism. It's now looking like it may be the fundamental glue that holds space together. In 2006, Shinsei Ryu and Tadashi Takayanagi showed something beautiful. They showed that in the ADS-CFT correspondence, the geometry of the bulk space-time is directly related to the pattern of quantum entanglement in the boundary theory. Specifically, the area of certain surfaces in the bulk, the ones that minimize their area subject to certain conditions, equals the entanglement entropy in the boundary theory. This is called the Ryu-Takayanagi formula, and it's telling us that geometry comes from entanglement. If you change the entanglement structure on the boundary, you change the geometry of the bulk. If you destroy enough entanglement, you can literally tear space apart. Space, in this picture, is woven from quantum entanglement. Let me give you a sense of the numbers involved. The amount of entanglement needed to create a single Planck area worth of space, about 2.6 times 10 to the minus 66 square centimeters, remember, corresponds to roughly 1 bit of quantum information, 1 qubit in the boundary theory. To create a region of space the size of a proton, about 10 to the minus 13 centimeters across, you would need on the order of 10 to the 40th qubits, all entangled in a very specific pattern. The observable universe, roughly 8.8 times 10 to the 26th meters in diameter, would require something like 10 to the 122nd qubits on the boundary. These numbers are staggering. The amount of quantum information needed to encode everything we see is finite, but almost inconceivably large. Could I be wrong about all of this? Of course. I've been wrong before. Every physicist has. And I want to be careful about the distinction between what we know and what we suspect. What we know: black hole entropy scales with area. The Bekenstein bound is real. Hawking radiation exists in the theoretical framework, and no one has found an error in the calculation in 50 years. The ADS-CFT correspondence is supported by thousands of consistency checks. Not a single one has failed. What we suspect but haven't proven, that the holographic principle applies to our actual universe, not just to anti-de Sitter space. That space in our universe is emergent from entanglement. That the three-dimensional world we experience is genuinely a projection from a lower dimensional boundary. Some people compare the situation to the early days of general relativity, when Einstein had the theory, but many of the observational confirmations, gravitational waves, black hole images, gravitational lensing, came decades later. I think that's a fair comparison. The mathematical structure is so tight, so self-consistent, so predictive within its domain, that it would be very surprising if it turned out to be completely wrong. It might be incomplete, it might need modification, but the core insight that information, geometry, and quantum mechanics are related in this holographic way, I'd be willing to bet a great deal on that. But I've been around long enough to be skeptical of certainty. Physics has a way of surprising you just when you think you've got it figured out. Newton's physics ruled for over 2 centuries before Einstein overturned it. Einstein's own intuitions about quantum mechanics, his insistence that God doesn't play dice, turned out to be wrong, spectacularly wrong, and in precisely the way that now underpins the holographic principle. Entanglement, the thing Einstein most distrusted about quantum mechanics, may turn out to be the most fundamental thing in the universe. That's not irony, that's physics. Let me tell you what I find most remarkable about all of this. When Bekenstein first proposed that black holes have entropy, in 1972, he was a graduate student. He was fighting against the establishment. Hawking himself initially argued against Bekenstein's idea. When 't Hooft proposed the holographic principle in 1993, many physicists thought it was too speculative, too far ahead of the evidence. When Maldacena published his paper in 1997, it took years before the community fully appreciated what he had done. Each of these ideas was initially resisted, and each of them turned out to be pointing in the same direction, toward the same astonishing conclusion, that the universe is not what it seems, that the three-dimensional space we navigate every day, the space we build our houses in and fight our wars in and fall in love in, is not the bottom level of reality. There's something deeper, something flatter, something more fundamental. And here's the really beautiful part. This isn't diminishing. It doesn't make the universe smaller or less wonderful. If anything, it makes it more wonderful. The fact that quantum entanglement can weave the fabric of space, that the geometry of the cosmos can emerge from patterns of information on a distant boundary, that's more remarkable than anything a pre-holographic physicist could have imagined. We used to think space was simple, a blank stage. Now we know it's a construction, an elaborate, intricate, beautiful construction built from the most subtle correlations in quantum mechanics. When I was younger, I thought the goal of physics was to describe what happens in space and time. Now, after decades of listening to what physics says, I've learned something different. The goal is to understand where space and time come from. We're not quite there yet. The holographic principle is a window, not a final answer. But it's the most extraordinary window physics has ever opened. And what we can see through it has already changed how we think about reality. Some people find this unsettling. The idea that the solid, tangible world might be a projection from somewhere else. That space itself might not be what it appears. I understand why that's uncomfortable. We're built to trust our senses. 3 dimensions is all we've ever known. But physics has been telling us for over a century that our senses are unreliable narrators. Atoms are mostly empty space. Solid matter is held together by quantum forces that have no everyday analog. Time passes differently depending on how fast you're moving. And now, space itself may be emergent. The universe doesn't care about our intuitions. It cares about its own deep mathematical structure. And that structure is telling us something we didn't expect. I've spent the better part of my career on this problem. From the early arguments with Hawking in the 1980s, through the string theory formulation in the 1990s, to the entanglement and geometry work of the last 15 years. It's been the most intellectually thrilling journey of my life. And we're still in the middle of it. The biggest questions: how does the holographic principle work in de Sitter space? How does time emerge? What is the boundary theory for our actual universe remain open? There's a lifetime of work left for young physicists who are willing to take these questions seriously. I'll leave you with this. The holographic principle started with a simple question about black holes and entropy. It led us to discover that information scales with area, not volume. That discovery led to a war about whether information can be destroyed. That war led to a radical new idea about the nature of space. And that idea led to what may be the deepest insight physics has produced in my lifetime: that the universe is not built from stuff in space, it's built from information. And the way that information is organized, entangled, correlated, encoded on boundaries we can barely conceive of, gives rise to everything we experience. The coffee, the chair, the stars, all of it, a hologram. Not fake, not an illusion, but not what it seems. After all these centuries, the universe can still surprise us with the simplest things. Thank you for listening.